Hey guys, so with this video we start the section on electronic structure and periodic properties of the elements. And this video talks about light. The reason we start with light is that what we're doing in this section is we're trying to figure out in an atom where the electrons are and what they're doing. And it ends up the only tool we have that can do that is light, also known as electromagnetic radiation. So electromagnetic radiation, it ends up as two parts, an electric part and a magnetic part. We don't really need to know at this point what a field is or anything like that. All we need to know is that there's two parts to light, an electric part and a magnetic part, and these are perpendicular to each other. So if this is light as a one-dimensional wave, then maybe the electric field component would be up and down the z-axis, and the magnetic part would be along the y-axis. So that's all we need to know is there's two parts to electromagnetic radiation, the electric part and the magnetic part, and those are perpendicular to each other. All right, so electromagnetic radiation covers a wide range of types, all the way from gamma rays up through radio waves. And what characterizes a certain type of electromagnetic radiation ends up being its wavelength or frequency. Those two are related, and I'll talk in just a minute about what specifically we mean by the wavelength and the frequency and how they're related. But what I'm trying to show in this picture is that there's a really wide range of types of electromagnetic radiation, from really, really short wavelength light, which is, this is in nanometers, so this is 10 to the minus 3 nanometers or 10 to the minus 12 meters, a picometer. That's really short. That's gamma rays. All the way up through X-rays, UV, visible light, infrared, microwave radiation to radio waves, which is 10 to the 13 nanometers, which is 10 to the 4th meters, or about 10 kilometers. So all the way from picometers to kilometers. It's a wide range. Of that entire range, guys, the only part of that electromagnetic radiation that we can see with our eyes, visible light, is a really, really small fraction. If this were to scale, we would not even be able to see the part that's visible light, because visible light goes from only 400 nanometers through 700 nanometers, right? A range of 300 nanometers. It's really, really small when we're going from 10 to the minus 3 to 10 to the 13th, right? But what you should get out of this, what I want you guys to know, is that the range of visible light, 400 to 700 nanometers, that the shortest wavelength light we can see is about 400 nanometers, and just underneath that, just a little bit shorter than that, is UV or ultraviolet light. And the longest wavelength light we can see is red, which is about 700 nanometers, and a little bit longer than that is infrared or IR, infrared radiation. Also, you should know the order of the colors. So we go from violet to blue to green to yellow to orange to red. And that's all. Okay, so properties of waves. Waves have wavelength, frequency, and amplitude. A wavelength is a distance from one peak of a wave to the next peak, or we can go from one trough to the other. So if you imagine you're standing there, two people holding each end of a rope, and you make a wave, right? That's a standing wave. So you can see the peaks that look like this, and the troughs, and the wavelength distance from one peak to the other, or one trough to the other. Amplitude is how high that wave is. So the higher up it goes, the greater its amplitude. Frequency is how many wavelengths pass through a given surface area per second. Another picture that really helps with this, I think, is if you imagine yourself standing on a beach and count how many times a wave hits your ankles. The number of waves that hit your ankle per second or per minute would be the frequency of that wave. So we have three waves here, A, B, and C. A has a longer wavelength than B, which is longer than C. And the frequency is how many of these wavelengths in a certain area. And so we can see that the longer the wavelength, the lower the frequency, and the shorter the wavelength, the higher the frequency. It's an inverse relationship, which we'll see in just a minute. So the reason that we're talking about waves when we're talking about light is that light ends up acting as if it's a wave. And the way we know this is something called the double slit experiment. And the way this works is if you imagine a wall with a little tiny hole in it, and we're shining light at that hole. If we have another wall right behind this, and forget about these openings for a minute, pretend this is solid, then we would just see, a beam of light hitting that wall, like a flashlight or something, right? But now if we put two small holes in this wall, then what we see on the wall behind that is something called an interference pattern. And the reason for that is that, first of all, waves have this property that they undergo something called constructive and destructive interference. The idea with this is that if you have two waves and they come together, if they line up so that their peaks are right on top of each other, then the resulting wave, it has a larger amplitude, higher peaks and lower troughs. That's constructive interference. However, if those two waves line up so that the peak of one is on top of the trough of another, they cancel out and it's actually flat. That's called destructive interference. And so what we see on this wall back here is we see an interference pattern. The bright spots are where there's constructive interference. The dark spots are where there's destructive interference. The reason for that is as this first light passes through the first slit, and then this light passes through the first slit, then it hits these two slits here. The light that comes out here comes out in these arcs, right? And then these are waves. It ends up, and so is this one. Where those waves overlap, if we have two peaks overlapping, we get constructive interference. If we have a peak and a trough overlapping, we get destructive interference. And so by the time it hits this wall over here, we see this pattern. So this is proof that light acts as, or electromagnetic radiation acts as a wave. So the relationship between wavelength and frequency for light is this. So in this equation right here, this is the relationship between wavelength and frequency for electromagnetic radiation. C is the speed of light in a vacuum. It's a constant. You should know that number. It's 2.998 times 10 to the 8th meters per second. We use lambda, which is what this is, the Greek letter lambda, to stand for wavelength. And in here, the units will be meters. And nu, this is a Greek letter nu, it stands for frequency. The units of frequency are 1 over seconds, seconds minus 1, which is what we call hertz. The symbol is capital H, lowercase z. And so you can see, because C is a constant, if lambda is big, then nu is going to be small. So if we have a long wavelength, we have a short frequency. Vice versa, if we have a short wavelength, we have a high frequency. So you should know this equation. An example of using it, pretty straightforward, is if we know that we have some visible light that has a wavelength of 529.3 nanometers. What's its frequency? Well, we use the equation here, C equals lambda nu. Because we're asked for the frequency, we rearrange the equation, solve for nu, C over lambda. And remember, the wavelength has to be in meters. So all I do is I take the wavelength that's given in nanometers, replace the prefix with what it means, and then times 10 to the minus 9th. I've got it. There's C. Meters cancel, only get 1 over seconds. So 5.664 times 10 to the 14th hertz would be the answer. All right, so another experiment that led to our current understanding of electronic structure in the atom is something called blackbody radiation. So you've seen blackbody radiation probably many times. Whenever you heat up a piece of metal and it glows, that's blackbody radiation. The old incandescent light bulbs, the way they work is by basically running a current through a tungsten filament. The resistance causes it to heat up and it glows, giving off light. So, back when they were trying to figure this stuff out, they were using classical theory. They hadn't developed quantum mechanics yet. And what they were using thermodynamics and classical electromagnetism. And what they were trying to do, so this would be what happens experimentally. What they noticed is that there's a relationship between the wavelength of blackbody radiation and it's the energy, right? So this spectral radiance, just think about it as the energy of the light. And so when they tried to model it with the current theories, that was the Rayleigh-Jeans law, they were able to model it for longer wavelengths light. This is the black curve right over here. But as the wavelength got shorter, so UV light, the theory did not match the experiment. That's why it's called the UV catastrophe. Then Planck came along, and Planck was able to develop a model that matched the experiment much better. So these lines are at different temperatures, but the blue line, think about it, this is Planck's theory, and it matched the experiment very well. And so it ends up that Planck had to make an assumption that was critical, that led to a much deeper understanding of what's happening. So one of the things Planck assumed, the important thing he assumed, is that in blackbody radiation, he hypothesized that energy can be gained or lost only in whole number multiples of some quantity that's related to the frequency of the radiation, and that was h nu. So what he said was this: the change in energy between two levels was equal to some integer times h nu. Now, what he's thinking when he came up with this is he was trying to figure out what's happening inside the atoms of that metal that's glowing. Say, well, you heat it up, so they're gaining energy, so they must have higher energy, and then they drop back down to their lower energy, and when they do, they give off light. That difference in energy he was thinking was light. And what he said was the light that came out, which was equal to the energy of that light was equal to the energy of the difference in energy of the electrons that's going from higher energy to lower energy, had to be equal to some multiple of h nu. Now h was a constant that was named after him because he discovered it, Planck. This is called Planck's constant. It's 6.626 times 10 to the negative 34th joules second. So memorize that number. Remember that is a symbol. Nu is the frequency of the electromagnetic radiation that's being absorbed or emitted, and n is an integer. So this was a radical assumption. This was the beginning of quantization, which is the beginning of quantum mechanics. So that's what Planck did for us. Okay, so Einstein also tried to explain another experiment that they couldn't explain, something called the photoelectric effect, made another contribution. So so first of all, what's the photoelectric effect? It ends up if you take two pieces of metal, put them next to each other but not touching inside a vacuum, so this is supposed to be a vacuum, and you hook up a battery, one pole to one piece of metal, the other to the other, and we put a meter in there to measure the current. Now, because these two pieces of metal are not touching, no current is going to flow, and this meter will read 0. There's no current passing through this circuit because it's not closed. Now, it ends up that if you take light and you shine it on this metal over here, sometimes you see a current, and the only way that could be is if there's an electron being emitted from this piece of metal and being attracted towards this electrode, and then so now we have a complete circuit. We have a current. But the thing that they could not explain back then was that no matter how bright that light, if the wavelength was less than a certain number, and that number depended upon the metal, then you saw no current whatsoever, no matter how bright that light was. And so their thinking was, well, the brighter the light, the higher the amplitude of the waves, and the higher the energy, right? So you shouldn't be able to, make it bright enough to kick off an electron, but they couldn't. But they found that once they reached some certain wavelength or frequency, called the threshold frequency, then no matter how weak that light that was hitting that metal, they would see a current. And so they couldn't explain this until Einstein came along, and what he said was critical. He said, what if these photons that are hitting this metal, what if this light that's hitting this metal is made up of little tiny chunks of energy they call them photons, right? So he's talking about light being a particle instead of a wave. He said, well, what if these little tiny chunks of energy were discrete, and so when each photon hit, each chunk of energy hit, if it had enough energy, it would kick off an electron, no matter how many photons there were, how many chunks of energy there were. And he said, okay, so he figured out that the energy of one of these chunks of energy, one of these photons, is equal to Planck's constant times the frequency. We just saw that with blackbody radiation. Planck's applying this to light, though, and that's equal to hc over lambda. So that's what Einstein said, and he was able to successfully predict what happens in this experiment. Now it ends up that law of conservation of energy tells us that the kinetic energy, how the 1/2 mass times the velocity squared of this electron that's kicked off, it's equal to the energy of the photon that hits that metal minus the amount of energy that it takes to rip that electron away from the metal. And that takes some amount of energy. The amount of energy it takes to pull that electron away from the metal is called the work function, and it's different for every different metal. The work function is also equal to h nu 0. That is, this remember, the energy of a photon is h nu. The energy of a photon that will just barely remove an electron from this metal with zero kinetic energy, that frequency of that photon is called the threshold frequency. Any frequency higher or shorter wavelength, and we get electrons. So that's what Planck said. So this equation right here, you guys should know, put it on your cards. The kinetic energy of the ejected electron, which is equal to 1/2 mass of the electron times the velocity of the electron squared, is equal to the energy of the photon that hits the metal minus the work function of that metal. So let's do an example. So we want to figure out how fast an electron travels when it's ejected from a piece of tungsten when a photon with wavelength 212 nanometers hits that metal in a vacuum. So it's a photoelectric effect. And things that we know are the rest mass of an electron is 9.109 times 10 to the minus 31st kilograms. And the work function of tungsten, the symbol for the element tungsten is W, so it looks funny, WW, but it's the work function of tungsten is 8.38 times 10 to the minus 19th joules. So why don't you guys go ahead and use that equation we just saw and see if you can figure this out. And when you get an answer, come on back. Welcome back. So here's my work. There's the equation we used. What I did was I first rearranged this equation and solved for v, the velocity of the ejected electron. So I multiplied through by 2 times this whole thing divided by m, and then I took the square root of both sides. Then I said, okay, so I need the energy of the photon, and that's equal to hc over lambda. We were given the wavelength as 212 nanometers, so this is Planck's constant times the speed of light divided by the wavelength in meters, so 212 times 10 to the minus 9th meters, and I get 9.37 times 10 to the minus 19th joules. We're given the work function for tungsten, and we know the mass of an electron. So we plug this in for m, this in for w, and we get 4.7 times 10 to the 5th meters per second. There we go. That's how you do it. So one last thing. Famous equation, right? E equals mc squared. So we also that means we can apply this to a photon. And so if the energy of a photon is equal to hc over lambda, that means that we can say that mc squared is equal to hc over lambda, or mass of the photon is equal to Planck's constant over lambda c. So this looks like a photon has mass, right? But it's not that straightforward. This is what they call relativistic mass. It's an old term, and people don't really use it that much today. We use what's called the invariant mass, or the rest mass, and that's 0 for a photon. So a photon has no mass, has momentum, and it gets really funky, but we don't need to worry about that. So we could calculate the relativistic mass of a photon of light. Let's say the light has a wavelength of 450 nanometers. Plug it into this equation right up here, and we get 4.82 times 10 to the minus 36 kilograms, which is really, really small. And that's not even really the real mass. That's just relativistic mass. check out the units here, okay? It's very useful. And to see how the units work out to kilograms, you'll need to remember that joules is really kilograms meters squared per second squared. That's all there is to that, guys.